In problem 6.52, you have an engine pulling on a mass to the right, and so this is the tension in the cable, F sub T. You have a normal force up, the weight down, and a frictional force in the direction opposite of the motion. The block is being moved at a constant speed, so the initial speed and the final speed are both 15 meters per second. Since the block is on the ground in both cases, that makes the potential energy initially and finally equal to 0. Because they have the same velocity in the initial position and in the final position, these cancel out. So they're not 0, but since their velocity and masses are the same, these two terms cancel out. There are two terms for the work. You have the work done by friction and the work done by the engine. So the work done by friction is simply just S times the frictional force times the cosine of the angle between the frictional force and the displacement. The displacement is from here to there. So there's the displacement, there's a frictional force, and the angle between those two is 180 degrees. That's one of the terms for the work. The other work term is the work done by the engine, and we'll just call that W sub E. And all of that's equal to 0. The frictional force is due to kinetic friction, so it's F times mu times the normal force, and the cosine of 180 degrees is -1. So that's plus the work done by the engine is equal to 0. Now we're given in the problem that the power from the engine is 40 horsepower, and you can convert that over to watts using 1 horsepower equals 746 watts. So you get a number here in watts. Oh, looks like I made a mistake here. This should be the normal force. So the frictional force is the coefficient of kinetic friction times the normal force. Okay. Now if you look at your free body diagram up here, you can sum the forces in the x direction, and you find out that the tension is going to be equal to the frictional force. If you sum the forces in the y direction, you find out that the normal force is equal to the weight because there's no acceleration up and down. So we can replace this term with the weight. So it's minus S mu mg. That is the weight of the mass. You also can realize that since power is equal to work divided by time, if we're given the power from the engine, then the work done by the engine in an amount of time t is the work by the engine divided by t. So solving for that and plugging it in here, you find out that it's plus power from the engine times time equals 0. Moving this to the other side, you find out that the power from the engine, not to be confused with potential energy, is equal to mu mg s over t. So I've moved this to the other side, and I've also divided by t. This is given in the problem, the mass is given in the problem, and g is given in the problem. And now I realize that what we're really looking for is the mass. So we don't really want to do this. Instead, you want to solve for the mass. M, moving this to the other side, is Pe over T divided by S mu G. Now cleverly hidden in here is potential energy, and then you can have S over T like this, dividing top and bottom by T, mu times G. S over T is also the velocity that was given in the problem. Here's the distance s that we traveled, which was arbitrary, but it also turns out to be the same length of time that we use here in our power equation. So it is a legal physics and mathematical maneuver to actually say that it's the power from the engine divided by the speed times the coefficient of friction times the acceleration due to gravity.